Okay, so this is going to be a review of first-order transients. So any first-order circuit can be reduced to this differential equation dx of t over dt plus x of t over tau equals k, where x of t is the sought voltage or current, such as the voltage across a capacitor or maybe the branch current. Tau is the time constant, which is going to be R Thevenin C or G Thevenin times L, depending on whether the circuit has a capacitor or an inductor. And K is going to be the constant input from the sources, which, using the idea of Thevenin equivalent and Norton equivalent circuits, is going to be VOC or ISC. So in order to solve this differential equation, we have to combine the homogeneous and the particular solutions. So let's first find the homogeneous or the natural solution. Okay, so this is going to be the response of the system when we bring it up to a certain point and then just let it go. So for example, in this case, that's going to be having a circuit in steady state and then opening or closing a switch and seeing how the system responds. So in order to find the homogeneous solution, we're going to set the input to be 0. So we'll rewrite the differential equation. Set it equal to 0. Now we can rearrange this equation, and we'll just use x for simplicity. So we have dx over dt equals negative x over tau. Now we can multiply the whole thing by dt over x so that we have dx over x equals negative dt over tau. And now we can integrate from here, we'll say x of 0 to x of t, and then on this side from 0 to t, and we'll change these to be dummy variables for integration. Solving these integrals gives us ln of x of t minus ln of x of 0 equals negative t over tau. And rewriting, we have ln of x of t over x of 0 equals negative t over tau. Apply the exponential to each side, and we're left with x of t over x of 0 equals e to the negative t over tau. And then this can be written more generally as x t equals constant a times e to the negative t over tau. That is our homogeneous solution. Now for the particular solution, because the input k is constant, we are going to assume that the particular solution is also constant. And we're going to call that constant b. Now we have to test this assumption. So we're going to plug it into our differential equation. and the derivative of a constant is just 0, so that cancels out that term. Now if we plug in b for x of t, that gives us, and we rearrange the equation, we have b equals k times tau, and this is a constant. Therefore, we were correct that the particular solution is a constant. So we have our homogeneous and our particular solutions. Now we combine them. Let's say x of t equals a times e to the negative t over tau plus b is our solution. And in order to figure out the values for a and b, we have to plug in our conditions, our final and our initial conditions. So in order to find b, we'll plug in the final condition, which is that as t goes to infinity, the exponential term goes to 0. Because of that, b is just going to be x of t as it goes to infinity. Then we plug in our initial condition, which is that at t equals, or as t equals 0 plus, the exponential e to the negative t over tau equals 1. Therefore, x 0 plus is going to be equal to a plus b. And rearranging, that's a equals x of 0 plus minus b. Therefore, since we already know b, a equals x of 0 plus minus x of infinity. Now writing this all out, x of t equals x infinity plus x of 0 plus minus x at infinity times e to the negative t over tau. We will use this equation as the solution form for our sought variables in our first order transient circuits. So in this circuit, we have an independent voltage source, an independent current source, a dependent voltage source, an inductor, a switch that closes at t equals 0, and we are asked to solve for IL of t. So first we're going to have to solve for IL of t at t equals 0 minus, then at t equals 0 plus, then I of L as t goes to infinity, and then we're going to find R Thevenin as seen from the inductor terminals. And then once we have all of those things, we can write the solution for IL of t. So first, we're going to solve at t equals 0 minus. So since the circuit is in steady state at this point, the inductor can be replaced with a short, and this switch will be open, which means that this dependent source will be hinged and can be removed from the circuit. So we have the 6 ohm resistor, the 1 volt voltage source, the 4 ohm resistor, the other 4 ohm resistor, 7 ohm resistor, and the 5 amp current source. And we still have our sought variable IL at 0 minus. And since the dependent source has been removed, we don't have to worry about the control variable Ex right now. Now we can simplify by combining the resistors. The 6 ohm and the 7 ohm resistors combine to be 13 ohms. And the 2 4 ohms combine to be 8 ohm. And now, in order to simplify further, we're going to have to transform this voltage source because it is in series with the resistor. We can transform it into a current source so that we have an entirely parallel circuit, so that we can eventually combine the current sources, and then we can have a current divider. So now I've rearranged the circuit. The value of the 13 ohm resistor stays the same, and the value of the transformed source is now going to be 1 volt divided by 13 ohms. So that's 1/13 amps, and it's pointed this direction to align with the way that it was up here. And then when we combine these two current sources, they are fighting, so it'll be the value of the current source will be 5 minus 1/13. So the new value of the current source is 4.923 amps. And now we just have a current divider, and we're looking for IL of 0 minus. So IL 0 minus equals, and it's pointing this direction, so positive 4.923 amps times, and we're going to choose the, on top for the numerator, the resistor, not the resistor next to the sought variable because of the current divider formula. So 13 ohms over 13 ohms plus 8 ohms, and that comes out to be 3.048 amps. And now we can solve for IL at t equals 0 plus, because that's the same value. So IL 0 plus equals IL of 0 minus equals 3.048 amps. So now we're going to solve for IL at t equals infinity. And we're going to go back to the original circuit. And since this circuit is in steady state again, the inductor is going to be replaced with a short. And the switch is going to be closed, so that will also be a short. So now we have our circuit at t equals infinity. We can combine these two resistors because they're in series. That's an 8 ohm resistor now. And we're going to use mesh analysis. We could use either nodal or mesh analysis, either way. We're going to use mesh analysis, so we'll choose the inner mesh here to be reference mesh. the outer mesh to be I1, this I2, and I3. So first, I'm going to write our current constraint equation. So I2 is going to be 5 amps. That's the only current constraint equation. Now for our mesh equations, we're going to be counting voltage drops. So for I1, we'll start with the 8 ohm resistor. So it'll be I1 minus I2 times 8 ohms. Plus I1 times 7 ohms. And then minus 5Vx minus 1 volt. And all of that equals 0. Now for I3, we have I3 times 6 ohms, and then plus 5Vx equals 0. Now for our control variable Vx, Vx is just going to be equal to negative I3 times 6 ohms. And then for our sought variable, which is IL of infinity, that's just going to be I2 minus I1. Now we have all of our equations that we need, and then we solve for this system of equations, and then our sought variable comes out to be 2.267 amps. So now we're going to find our Thevenin as seen from the inductor terminals. The first thing we're going to do is kill the sources, and this voltage source is going to be replaced with a short, and this current source is going to be replaced with an open circuit, and also this is for t greater than 0, so the switch is going to be closed. And we cannot kill our dependent voltage source. So now this is what our circuit looks like. If we didn't have this dependent source, we could just look into the terminals of the inductor and find our Thevenin pretty easily. But since we do have a dependent source, we can't get rid of the inductor, but we have to replace it with a current source. And then when we find the voltage and current supplied by that current source, we can use that to find our Thevenin. So I'll redraw the circuit. So I've redrawn the circuit here, and we can see that these three resistors can be combined into a 15 ohm resistor because these three are in series. The inductor has been replaced with a current source, and we're going to, for the value of that current source, we're going to use the value of IL at 0 plus, and that's going to be 3.048 amps. And then our sought variable will be the voltage supplied by the source. We have our 6 ohm resistor, the control variable Vx, and our dependent source. So now for this, in order to find our sought variable Vs, we're going to use nodal analysis. Again, you could use mesh or nodal analysis, but I've chosen to use nodal analysis. And this will be the ground, the reference node. And then this can be V1, and this node V2. So first, we'll write our voltage constraint. And that'll be V2 is constrained by this dependent source to be equal to 5 Vx. So V2 equals 5 Vx. And our node equations, we'll say, we'll count currents pointing out from the node. And V1, for V1, for the 15 ohm resistor, that'll be V1 minus V2 over 15 ohms. And then minus 3.048. amps. That's equal to 0. And we have our control variable, Vx. Now Vx is just going to be V2 minus 0 between those two nodes. So that Vx equals V2. And then sought variable, Vs, is just going to be equal to V1 minus 0. So V1. In solving this system, we find the voltage supplied by the current source to be 45.72 volts. And then R Thevenin is just going to be equal to Vs, or the voltage supplied by the source, over the current supplied by the source, 45.72 over 3.048. And that's going to be equal to 15 ohms. So R Thevenin is 15 ohms.